Good day everyone. Myself Vaidehi working as assistant professor in Sri Muthukumaran Institute of Technology, Mangadu. Today the video lecture is from the subject EC3452 Electromagnetic Fields. The topic is from the Unit 1 Introduction Unit. The topics we are going to see is Helmholtz theorem and the understanding of the vector decomposition. Before going to the topic, let's see about the introduction about the Helmholtz theorem. Helmholtz theorem formulated by Hermann von Helmholtz is one of the most powerful and elegant results in vector calculus. It provides a systematic way to analyze any vector field by breaking into simpler meaningful components. In electromagnetic field theory, vector quantities such as electric field intensity and magnetic flux density often appear complex and difficult to interpret directly. Helmholtz theorem tells us that no matter how complicated a vector field appears, it can always be decomposed into two functional parts. This principle forms the mathematical backbone for potential theory and greatly simplifies the study of electromagnetic fields, fluid motion, and many other physical systems encountered in engineering. Let's see about what is Helmholtz theorem. Helmholtz theorem states that any sufficiently smooth vector field defined in three-dimensional space can be uniquely decomposed into two components, a curl-free component and a divergence-free component. The importance of this statement lies not only in decomposition but also in uniqueness. This means that for a given vector field, there is only one possible way to separate it into these two components under proper boundary conditions. In electromagnetic theory, this allows us to represent electric and magnetic fields in terms of scalar and vector potentials. Therefore, the theorem provides both a theoretical foundation and a practical tool for analyzing field behavior. In that, we see about the irrotational part. The irrotational part of a vector field is the component whose curl is equal to 0 everywhere except possibly at singular points. Because its curl is 0, this component has no rotational or swirling behavior. It is expressed mathematically as the gradient of a scalar potential function. Such fields are known as conservative fields because the work done by the field along a closed path is zero. In electrostatics, the electric field due to stationary charges is irrotational and can be derived from the electric scalar potential. This shows how Helmholtz theorem naturally connects with the physical interpretation of electrostatic phenomena. Next, we see about the solenoidal part. In solenoidal part of a vector field is the divergence free component, meaning its divergence is zero throughout the region. A zero divergence implies that there are no sources or sinks within the field and a field lies from the continuous closed loops. This component is mathematically expressed as the curl of a vector potential. In magnetostatics, magnetic fields are classic examples of solenoidal fields because magnetic field lines never begin or end. They always form closed paths. This divergence free nature reflects the non existence of magnetic monopoles. Thus, the solenoidal component captures the purely rotational characteristics of a vector field. Next, we see the intuition behind the theorem. In that, first we see about the sources and the sinks. To understand divergence-free behavior intuitively, imagine water flowing in a perfectly sealed pipe system. There are no taps adding water and no drains removing it. The amount of water entering any region is exactly equal to the amount leaving that region. This is similar to a solenoidal field where the divergence is zero. There is no net creation or destruction of field lines within the region. This physical analogy helps us visualize why the divergence free component represents continuously loop like behavior in the field. In that next we see about the circulation and vortices. Now consider irrotational fields. If you observe smooth laminar flow in a straight river with no whirlpools or swirling motion, the particles move forward without rotation about any point. This represents a curl free or irrotational field. The absence of curl means there is no circulation around any closed path. In such fields, the line integral around a closed path becomes 0. This explains why conservative fields can be represented using scalar potentials. The absence of rotational motion makes the field mathematically simpler and physically predictable. Next we see about the combined behavior. In most real world systems, vector fields are not purely irrotational or purely solenoidal. They exhibit both divergence and curl simultaneously. For example, fluid motion in nature may contain both vortices and inflow or outflow regions. Helmholtz theorem tells us that such a complex field can always be separated into two simpler parts, one representing source or sink behavior and the other representing rotational behavior. This separation allows engineers to analyze complicated field patterns in a structured and logical manner, making problem solving more manageable. Next, we see about the mathematical statement. Mathematically, Helmholtz theorem states that any vector field f of position r can be written as the sum of the negative gradient of a scalar potential pi and the curl of a vector potential a. The scalar potential is obtained from the divergence of f and the vector potential is obtained from the curl of f. The uniqueness of these potentials depends on suitable boundary conditions and smoothness of the field. This mathematical formulation transforms a difficult vector field analysis into potential based equations, which are often easier to solve standard techniques in electromagnetic theory. In that, first we see about the scalar potential. The scalar potential pi represents the irrotational component of the vector field. By taking the negative gradient of pi, we obtain the curl-free part of the field. In electrostatics, the electric potential is a scalar quantity measured in volts and the electric field is obtained as the negative gradient of this potential. This shows how Helmholtz theorem provides the theoretical justification for expressing electric fields in terms of voltage. The scalar potential simplifies the understanding of conservative fields and reduces the complexity of field calculations. In that, next we see the vector potential. Vector potential A represents the solenoidal component of the vector field. When we take the curl of A, we obtain the divergence free part of the original field. In magnetostatics, the magnetic field B is expressed as the curl of a magnetic vector potential A. This formulation is extremely useful in solving magnetic field problems because it automatically satisfies the divergence free condition. The concept of vector potential also plays a central role in advanced electromagnetic theory and wave propagation analysis. Next we see about the verification of Helmholtz theorem. To verify Helmholtz decomposition, we use fundamental integral theorems of vector calculus such as the line integral, Stokes theorem and the divergence theorem. These theorems connect local differential properties like divergence and curl to global integral quantities like circulation and flux. By applying these theorems over different geometrical regions, we can confirm whether a given vector field behaves as predicted by Helmholtz theorem. This systematic verification ensures both mathematical correctness and physical consistency. Next we see the example 1 for irrotational field verification. Consider a vector field defined as F equals negative gradient of a scalar potential pi equal to 1 divided by r. This represents an inverse square field similar to the electrostatic field of a point charge. When we compute the curl of this field, we obtain 0 everywhere except at the singularity. Evaluating the line integral around any closed path also gives 0, confirming that the field is confirming the field is applying the 0 everywhere except the singularity. Evaluating the line integral around any closed path also gives 0, confirming that the field is conservative. Applying Stokes' theorem further verifies that the surface integral of the curl over any bounded surface is 0. Hence, this example clearly demonstrates the irrotational nature of the field. Next, we see about the example 2 for solenoidal field verification. Now, consider a vector field defined as the curl of a vector potential A equal to r divided by r cube. The divergence of this field is 0 because the divergence of a curl is always 0. When we evaluate the flux of this field through any closed surface, the net flux becomes 0, confirming the absence of sources and sinks. The divergence theorem further validates this property. Therefore, this example clearly illustrates the solenoidal or divergence free field of the field nature of the field. Next, we see about the verifying the uniqueness and the different paths and surfaces. The uniqueness of Helmholtz decomposition can be verified by testing the vector field over different paths, surfaces, and volumes. When the line integrals are computed along circular, rectangular, or irregular closed paths for irrotational fields, the circulation always remains 0. Similarly, surface integrals of solenoidal fields yield consistent results irrespective of the surface shape. This consistency proves that the decomposition is not dependent on geometry but is fundamentally determined by the divergence and curl of the field. Next, we see about the practical implications and the applications. Helmholtz theorem has wide-ranging applications in electromagnetic theory, fluid mechanics, and numerical simulations. In electromagnetics, electric fields are expressed using scalar potentials and magnetic fields using vector potentials. In fluid mechanics, fields are separated in potential and vortex components in computational methods. Helmholtz theorem decomposition improves stability and accuracy when solving partial differential equations. Thus, the theorem is not only theoretically elegant but also practically indispensable in engineering analysis. Next, we see the summary. To summarize, Helmholtz theorem guarantees that any sufficiently smooth vector field can be uniquely decomposed into irrotational and solenoidal components. This decomposition is mathematically rigorous and physically meaningful. By connecting divergence and curl with scalar and vector potentials, the theorem provides a powerful framework for analyzing complex field behavior. Mastering this concept is essential for a deeper understanding of electromagnetic field theory and advanced engineering applications. Students, I hope you all understood everything. Thank you.